Hello, and thank you for joining me for today's lesson on motion basics and the intro to motion terminology. So today's section is measuring motion, which is the first section in our motion unit. And we are going to talk about a couple different things today. So to start with, learners will be able to identify or to define distance, displacement, speed, and velocity, and know the differences between those words. Learners will also be able to explain why the distance an object travels and its current displacement are not always the same. And last but not least, they will be able to describe differences between speed and velocity. So to start with, we are surrounded by moving things. Almost everything we see around us is moving in some way, shape, or form. And this is motion, which is an object's change in position relative to a reference point. And so to get this and understand this, we have to know what a reference point is. So kind of background, some background knowledge we need. A reference point is any object that you are comparing your motion to, something that stays in place while the object you are observing is moving. For example, a ball is thrown through the air. And the only reason you know that a ball goes from this person, draw legs instead of a ball there. A ball goes from this person to this person is because there are objects like trees in the background that the ball is going to fly between. And so you'll see the ball's position relative to the tree change. Okay? Or maybe there's a sidewalk, or there's grass on the ground, or there's clouds in the air. Those are all reference points. That's something we see as fixed, and this ball is moving relative to that. So the ball is then going to get to our second person. So a frame of reference. So that's a reference point. This object that we see is a reference point. A frame of reference. This is a system for specifying the location of objects in space and time. And it's a system for specifying the location of objects in space and time. This is essentially looking at what reference points are you looking at to measure your motion. That's our frame of reference. So you have a specific frame of reference, something that you're comparing motion to, something that you are comparing a position to. Which is why if you and a friend watch the same thing happen from two different angles, you see it as happening differently, because you have different frames of reference. You have different perspectives on it, essentially. So for example, trees can be used as a frame of reference to describe the motion of the snowboarder. In this picture here, we have trees in the background. We know that the snowboarder is moving because he's moving compared to the trees. We also have the ramp itself has fixed points. There's metal pieces in the middle that aren't moving, and you can see the snowboarder get closer to and farther from those different points. And we can describe motion in various different ways. We can use our cardinal directions, our north, south, east, and west, or we can use general terms like up, down, left, and right. All of those work to describe motion. When we're talking motion, one thing we have to have is we have to have a distance. So an object has to be moving, there has to be a distance that the object travels. And so when we refer to the word distance, we are talking about the path an object has taken. So the distance an object travels is equal to the path that it has taken. And that's what we use, and we're going to use that for our speed calculations. We have to have a distance. For example, the distance from Grand Island to Doniphan is roughly 12 or 15 miles, depending on where you go from. We'll call it 15 miles. Okay? So distance measures straight line path. Distance from Grand Island to Lincoln is 90 miles. But in addition to knowing distance, we need to know direction. There's got to be a direction involved in that too. And so, for example, if you start at home and drift around, let's change that. You start at home and drift around your neighborhood, change your directions a few times. If we attached a string to you, or we had you walk through paint before you started going, your footprints would show the path that you traveled, which would be the distance that you traveled around your neighborhood. Would be either one, that string, or two, your footprints with paint. And that is distance. We also have another method of specifying motion, and that is called displacement. Now, displacement is the change in an object's position. So this is different than distance, but displacement is the change of an object's position. And so while distance measures how far an object moves along a path, displacement refers to how far it is between the starting and ending points. For example, this diagram over here on the right, we have an athlete running around the soccer field. So they started at this point right here, and they went all the way over to this sideline, down to the other goal line, across, and back this way. If distance would be attaching this string. So this string would indicate your distance. Your displacement is how far it goes from your starting point to your ending point. So I started where I put this first mark and I ended here. They ended here. So my displacement is going to be this distance from A to B. This little bit's going to be my displacement. This whole path over here, all of this is going to be my distance. So thinking, which one of those is going to be bigger? Distance or displacement? Well, in this case, it's going to be distance. You traveled much farther distance than you did to get to where you ended at from where you started. And distance is always, the closest they will ever be is equal. So for example, if this person ran a straight line from here to here, their distance would be this far. Their displacement would also be this far. In that case, they would be equal. Otherwise, displacement is always less than distance, or distance is always greater than displacement. But it's really important to remember and to note that your displacement, one, it's often shorter, but two, it must always include, so it's often shorter and it must always include direction. So for example, we could say this direction, we could use cardinal directions. We can assume this is here. So this would be 10 yards to the east. Or we could say it's 10 yards to the right of the goal, standing from our perspective here. That gives us a direction to base our motion off of, which is what we need. Continuing on, again, direction always has to be given when it comes to displacement. But let's say the distance between your home and the school is 12 blocks. That information doesn't tell us whether you're going towards or away from the school if we say that you walked 12 blocks. Now, if we said that you went 12 blocks towards the school, now we have a displacement. So displacement indicates direction, such as in the case above, 12 blocks towards the school. And that's going to be really important here coming up in this unit. Along with distance and displacement, we have these other terms that we're going to use. One of them is speed. Now, speed describes how fast an object moves. Speed describes how fast an object moves, and this is done by taking the distance traveled and dividing it by the time interval over which the motion occurred. So we set this up as an equation, which is speed is equal to distance divided by time. This is going to be the equation we're going to use in this class, and we're going to use it quite frequently for a little while. In a couple videos, I'm going to talk about graphs. We're in a graph motion. But on a graph, if we graph distance versus time on a graph, we can find the slope of this line and we can calculate the speed. So the slope of a line on a distance versus time graph is equal to the average speed of that object. Down below here are just some examples of different speeds that objects travel at. For example, a person walking might travel 1.4 meters per second. A wheelchair racer might be 23 or might be 7.3 meters per second. A horse would be 19. A high-speed train would be 67. A race car would be 96, and and a jet can be upwards of 257 meters in 1 second. Okay, so continuing on here. Sometimes just knowing the speed of an object is not sufficient, and we need to know the direction as well. For example, in 1997, there was a lion escaped from a zoo in Florida. This lion got out and was then tracked because obviously it poses a health risk to people. So a helicopter crew was sent up into the air to guide searches on the ground and bring the lion in, sedate him, and bring him back to the zoo. So what ended up happening is the helicopter crew had to provide a velocity of the lion. They couldn't just give a speed. Hey, he's moving at 5 miles an hour. That's not going to help anybody, because the first question coming back is going to be where, which direction, which way. So we can give the velocity of an object. So the velocity is the speed of an object in a particular direction. And there's actually two ways you can define or calculate velocity. One is you can have the speed of an object in a direction. So you can have speed plus direction. Or, because we just talked distance and displacement, we said displacement always has to have a direction. So for velocity, we can take displacement and divide it by time to get our velocity as opposed to our speed. In the case of the lion's velocity was reported to be 4.5 meters per second to the north. So we have a speed, we have 4.5 meters per second, and we have a direction which is to the north. Or they could also report it as 2.0 kilometers per hour, either to the north or towards the highway, assuming there's only one highway in the general area. Those are both directions. It doesn't have to always be cardinals, your northeast, southwest. It can be generals or relatives, such as towards the highway, towards the school, away from the park, can all be directions for velocity. So again, as a reminder, speed tells us how fast an object moves. Velocity tells us both the speed of the object and the direction the object travels in. So that is our difference between speed and velocity. Because we have to use direction with velocity, we have to describe it relative to a reference point. Remember your reference points. Those are the fixed points that we compare motion to. So again, we can use our cardinal directions, our northeast, southwest, in terms of directions there. We can have an angle from a fixed line. So at 30 degrees north of the highway. We can use any number of these. We just have to have a way to specify the direction. And then last but not least, when we do this, we need to have positives and negatives along a line of motion. Typically, in general, if an object is moving, if motion is shown as being up and to the right, up and or to the right, we consider that positive. So down here it shows you positive in general is deemed as being in the vertical direction or up. And now on a graph we always indicate right as being positive, which then would make left and down negative. Does not matter if you do it that way or not. It just matters that you have one direction positive. So again, one direction's got to be a positive velocity. If it moves in the opposite direction, it's got to be a negative velocity. That's the important piece. That's the vector component of velocity. For example, if you have two velocities, we have what's called a combined velocity or a resultant velocity. Either one of those terms kind of works here. So let's say you're riding on a bus, traveling east at 15 meters per second. Welcome to the bus, traveling east at 15 meters per second. You and everybody on this bus are all moving at that velocity of 15 meters per second to the east. Now let's say that you decide to stand up. So we're going to cut the side off of our bus. We're going to watch you walk to the back. Hey, if you walk to the back, not down, but to the back, with a velocity of 1 meter per second, your bus is still going forward with 15, but you're going backwards at a velocity of 1 meters per second. So to find your resultant velocity, your new velocity, compared to a person standing over here watching on the ground, if they see this, it's going to look like you are moving at 15 meters per second to the east minus 1 meter per second to the west, or plus a negative 1 meter per second to the east. So you're going to be moving at 14 meters per second still to the east because this is such a greater quantity. So the bus is going to move this way, but you are walking towards the back, which drops your resultant or total velocity by 1 meter per second. Okay, here's a couple review questions. Make sure you can answer these before you call it a day. But after that, I will see you guys tomorrow. So the first question, what is the difference between distance and displacement? So you should be able to tell me what is the difference between those two terms, distance and displacement. Second one, I want to know what is the difference between speed and velocity. So how are these two terms different? What makes them different? And remember, there are two ways that you can calculate speed and velocity, so two quote-unquote differences between those two. Thank you guys for your time and attention. Enjoy the rest of your day, and I will see you all tomorrow.